Okay, so we're going to start looking at the new section on probability. And probability, as you're probably already aware, is the measurement of chance. What's the probability of rain tomorrow? What's the probability of my horse winning a race? What's the probability of me getting a H1 in honours maths, which is very high for all of you, of course. So it's kind of a measure of chance. In one sense, we could also say that probability is the measurement of randomness. Now, that almost is self-contradictory. You're measuring something that you can't predict. Well, it tries to put a bit of manners on randomness, and it tries to predict what's going to happen by means of very, very simple rules, the most fundamental of which is the fundamental principle of counting, which we'll move into in a few seconds. But there are some key terms that we need to know, and these key terms will keep popping up over and over and over again. First of all, as we said already, it's a measurement or a study of randomness. So randomness is going to be a key feature in all of these things. You know the way when a magician asks a person, pick a card, any card, yeah, they're all down. There's 1 out of 52 chances of picking any of the cards there. So that would be an example of probability. A sample space is where all of the possible outcomes are thrown into. So if I was to ask you, for example, to take 2 die, to throw them, and then to tell me what the product is on both of those, you could design a sample space by putting 1 to 6 down on the left hand side, 1 to 6 across the top of the grid, and then the products all into the boxes, the grid underneath. That would be your sample space. Each operation study is called a trial, or I prefer to call them an experiment, and not an experiment in terms of chemistry or biology, but an experiment in terms of picking a card, or throwing a die, or tossing a coin, or something along that way, out of which you will get a result. Okay, and the results, all the results that you get, are called your outcomes. So for example, if I told you to toss a coin 10 times and you got 4 tails and 6 heads, that would be your outcome. Now, if I said to you, throw a coin 10 times, and how many times do you get tails? Well, then that would be what we would call your event. Your event is your set of successful outcomes. So if I was to throw a coin 10 times, and if I was to get 7 tails and 3 heads, then 7 tails would be my event, because it would be my successful outcomes if I was interested in the number of tails that we're going to get. Okay, so let's begin with the fundamental principle of counting. The fundamental principle of counting is nothing more than the counting rule. Okay, what it does is it allows me to count very quickly, or calculate very quickly, the number of outcomes in a permutation, which is an arrangement, or in a probability question. So, for example, if one trial has m possible outcomes, and a second trial has n possible outcomes, then the total number of possible outcomes is m times n. Now, if you don't understand the jargon there, think in terms of the following. You go into your favourite clothes shop, and you notice they have a sale, and on one side they have 5 pairs of jeans reduced, and over the other side they have 3 t-shirts, and you only have enough money for one of each. You could pick the first pair with any of those 3, or you might pick the second pair of jeans with any of those 3 t-shirts, etc. So what you notice is each one of the 5 jeans can be paired off with any one of the 3 t-shirts. So if there are 5 jeans and 3 t-shirts, very quickly, that's 15 different pairs. That's 15 different permutations, 15 different arrangements that you could have in that particular situation. Okay, so for example, in a restaurant, there are 4 choices of starters, 3 choices of main course, 2 choices of dessert, and 4 choices of starters. How many choices of meal will you have? So let's read it again. In a restaurant, there are 4 choices of starters. Okay. There are 3 choices of main course. Fine. And there are 2 desserts. Now, let's go back and think about that. Any one of these 4 can be taken with any one of those 3 and any one of those 2. So you might decide to take the cod with the lamb and the ice cream. Or you might decide to take the mushrooms with the beef and the ice cream, etc. So very quickly what you begin to realize is that any one of those can be matched up with the 3 main courses and the 2 desserts. So therefore the quickest way to do this is to bring in the fundamental principle of counting and say there are 4 starters, there are 3 main courses, there are 2 desserts. 4 3s are 12 times 2, So that means that there are 24 different arrangements of a meal that you could have on that particular menu. Okay, so what is a permutation? A permutation, that's the proper mathematical word for an arrangement. So if you want to take 10 pictures in your mother's house and you want to arrange them on the wall, each different arrangement is one arrangement. So therefore, if you have 10 pictures and you put them into a certain arrangement, that's one permutation. If you change them around, that's the second permutation. So we're going to be interested in, well, how many permutations could we get altogether? And that's where the fundamental principle of counting comes in. Now, just before we start this thing, listen carefully to the questions that will involve the word arrange or arrangements, because straight away, they will always be a permutation question. Take, for example, 6 horses here. All right, so we've got 6 horses in the race. You could ask yourself, how many different ways could this race be finished if there were no dead heats between the horses? Well, you might have first, second, third, fourth, fifth, sixth, or you might have 1, second, third, fourth, fifth, sixth. In other words, it gets quite complicated quite quickly. So let's see if we can put a bit of manners on this from mathematics. Let's start easy. Let's start with A, B, and C. How many different ways can the letters of A, B, and C be arranged? Well, let's have a look. A with B with C, or A with C with B. Yeah, B with A and C, B with C and A. Now just to speed this up a little bit, I have a diagram here very quickly. Same as what I've had already. A, B, C, A, C, B. B then with any permutation of A and C, and C with any permutation of A and B. So very quickly you're noticing, if I start off with 3 letters, I get 6 different permutations or arrangements. Now, why is that the case? Well, we could look at it this way. They are the 3 spaces into which the letters A, B, and C are going to be placed. So you have A, B, and C in your hand, okay? You've got 3 letters that could possibly take first place. Now, only one of those 3 will actually be in first place, leaving 2 available for second place, out of which 1 will fill that position, leaving 1 behind. So straight away, the fundamental principle of counting tells us that there's 6, and that's a far easier way to do these type of questions than to have to write out a huge big rigmarole or to draw a tree diagram. If you want to do it, knock yourselves out, but I think the fundamental principle of counting where you use boxes is a much easier way to do these things. If I take the word maths, how many ways are there of arranging all the letters? Now, first of all, how many letters are in the word maths? 1, 2, 3, 4, 5. There are no restrictions. So straight away, we notice that we have 5 spaces. 1, 2, 3, 4, 5. Now, you have the 5 letters in your hand, so therefore all 5 letters can take first place. One of those will eventually take that position, leaving 4, leaving 3, 2, and 1. So the quickest way to do that is by means of the boxes. That's 20, 60, 120 different ways. And so that's exactly what we asked to do. Using the boxes there, let me just remove that handwriting. And let's do it again. So 5 of those can go into the first place, 4 into the second place, 3, 2, and 1. And when we multiply them, as we said already, we get 120 different ways. Now, of course, you could write out all the different permutations if you wanted to. However, that'd be very tedious. So I would suggest that when you're asked to arrange things, use the box method, fill the boxes in with the elements that are allowed to take each position, and just multiply them in order to get the total number of permutations. Now, notice what I did with the ABC. Notice what I did with the letters in the word maths. When there's no restrictions, you notice that for A, B, and C, it was 3 by 2 by 1. For maths, it was 5 by 4 by 3 by 2 by 1. That's an interesting mathematical function in itself, because that's called a factorial. And a factorial is nothing more than a number multiplied by every natural number below it. Now notice I say natural number, because natural numbers will automatically end at 1. If we were to go back to 0, then every factorial would be 0, and that would be quite useless. So a factorial is where you take any number and multiply it by every natural number below it down to 1. And that is the quickest way of finding out how many different arrangements or permutations of a certain number of letters or a certain number of horses can be arranged. When n objects are to be arranged with no restrictions, then we use n factorial. Now notice the factorial symbol itself is like an exclamation mark, and it is on your calculator. I'll show you where in a moment, but it's actually called factorial multiplication. So for example, 7 factorial, 7 by 6 by 5 by 4 by 3 by 2 by 1, which is 5040. Therefore, for any number, as I said already, any number n factorial is the number itself multiplied by the number before it, multiplied by the number before that, right the way back through multiplication to 1 itself. But the lovely thing about this is that if you just take a look at 7 factorial is all of these numbers multiplied. But 7 factorial contains 6 factorial, which contains 5 factorial, which contains 4 factorial, which contains 3 factorial, which contains 2 factorial. In other words, every factorial contains every other factorial below it. And that's going to come in very, very handy when we want to simplify factorial division or factorial multiplication. So just as an example, take 7 factorial divided by 5 factorial. Here I tell you it's 7 by 6, but I don't tell you why. But I want you to watch. What is 7 factorial? It's 7 by 6 by 5 by 4 by 3 by 2 by 1. And what's 5 factorial? 5 by 4 by 3 by 2 by 1. Do you notice anything? 7 factorial contains 5 factorial. So therefore they cancel, leaving you at 7 sixes, which are 42. And factorials are designed to do that, to involve cancellation, to make things nice and easy. Okay, so where is it? I've just covered it up with text. So let's remove the text and have a look. You can see where the button itself is. If you can find the mode button on your calculator, and then underneath the mode button is what we call the reciprocal button. Well, it's the second function or the shift function for the reciprocal button, and that will give you the what we call the factorial function. Okay, let's take an example. 6 horses, back to our 6 horses again, the ones we had at the beginning. 6 horses enter a race. How many ways can the race be finished, and assume that dead heats are not possible? Now, if there are 6 horses in a race and they're all to finish the race, then there are 6 spaces to be filled. All 6 horses are available to take the first position. Now, out of those 6, only 1 will come first, obviously, leaving the remaining 5 for second position, out of which one of the horses will fill that, leaving 4, then leaving 3, then leaving 2, and leaving 1. And the fundamental principle of counting says multiply them. 6 5s, 30. 34s, 120. 360, 720. So the answer is 720 different ways. So we can use, as we call this, fundamental principle of counting, or you can also use the factorial method. Take a look. 6 by 5 by 4 by 3 by 2 by 1, 6 horses, what's that? That's nothing more than 6 factorial. And on your calculator, if you tap in 6 factorial, you actually get 720. Okay. Now, what happens when we put restrictions on our permutations? So at the moment we're saying, okay, here's 10 objects, arrange them. Here's 5 objects, arrange them. Here's 4 horses, arrange them. Yeah, here's 10 paintings or 12 paintings, arrange them. But what happens when I become very pedantic and say, no, well, I actually want the 2 pictures on the outside, the red one and the black one. I don't care what you do with the ones in between. That's where the boxes are going to come into their own and make life very, very easy. So let's take an example. Up to now, there are no restrictions placed on any of the arrangements, and all the elements were used in n factorial. That's the easiest way to calculate all permutations. When restrictions arise, it's best to envisage the spaces to be filled as boxes and then simply place into each box the number of elements that are allowed into each position. So let's take an example. A number plate is to consist of 3 letters on the alphabet followed by 2 digits from 0 to 9. If no digit or letter can be repeated and 0 can never be used as the first digit, how many different plates can be manufactured? Now, listen to it again. A number plate is to consist of 3 letters followed by 2 digits. So in other words, there are 5 spaces to be filled. There they are. Okay. 3 letters into the first places. How many letters in the English alphabet? Yeah, go on. 26. Good. So 26. Now out of those 26, one of them will take first place, leaving the remaining 25, of which one will be used up, leaving 24. So there's your letters taken care of. What does it say then about these 2? And there's a bit of a restriction here because these 2 represent your numbers. They are to be filled with digits 0 to 9, but look, 0 can never be used as the first digit. So this can't be 0. Now, I hope you do know that there are 10 digits between 0 and 9. Yeah, so that means there normally would be 10 in here, but 0 is not allowed in this box. So that leaves 9 digits available to take the position. One of those will be used up. That leaves me with 8 for the second box. However, 0 is allowed back in again, which brings it back up to 9. So therefore now we've got a massive big calculation of 26 by 25 by 24 by 9 by 9, which brings us up into the millions, I think. Yeah, it does. It brings us up into 1,263,600. Okay, so that's the number of ways that I can get number plates from 3 letters of the alphabet and 2 digits, if 0 can never be used as that particular first digit. So let's just remove that and bring the boxes up again one more time. So again, 5 spaces to be filled, 3 letters, there they are, 2 digits, there they are. Okay, the 3 letters, 26 by 25 by 24, the 2 digits, 0 to 9, but 0 can't go in there, so that means it's 1 to 9, which is 9 digits. One of them used up brings us down to 8, but 0 goes back in, bring that up to 9, and that's where your multiplication will give you that wonderful figure of 1,263,600 different ways, which if you're a company making reg plates means you're not going to run out of them for quite a while. Okay, let's take another one. 2 adults and 4 children stand in a row for a photograph. How many different arrangements are possible if the 4 children are between the 2 adults? Now, 2 adults, 4 children. That's 6 people altogether. 2 and 4. That's 6. So there's your 6 spaces down here. What do we notice? What's the condition? How many different ways are possible if the 4 children are between the 2 adults? So there's adult 1, there's adult 2, and there's the 4 children. Now, many adults? 2 adults. So any one of the 2 adults can take the first place. One of them will take it, leaving 1 for the other end. And then the 4 children, any one of the 4 can go there, which reduces that down to the remaining 3, then 2, and then 1, which gives me 2 4s are 8, 24, 48, 48 different ways. Okay. Now, on your calculator, there is a little function button that allows me to do this. However, we only use this button when the number of elements that I'm using is greater than the number of spaces available. So for example, say you're moving into a smaller house. Say you originally had 10 pictures on the wall and now there's only space for 4. How many different ways could I use 4 out of those 10 on the smaller walls in my particular house? Now in a situation like that, what we're saying is out of the 10 we're picking any 4. See it? Out of the 10 we're picking any 4. So we only use this function when the number of spaces available to fill is smaller than the number of elements I have to fill that particular space. Okay, so for example, I have 7 pictures ready to hang, but I've only got 3 spaces. How many different ways can I fill the 3 spaces with 7 pictures? Okay, I only have 3 spaces. There they are. Now, how many of these pictures can I put into the first place? 7. One of those will be taken up in that space, leaving me with 6 and leaving me then with 5. 7 6s are 42, and 42 times 5 is 210. Of course, we could also say that out of the 7, I want to pick any 3. See it there? Out of the 7, I want to pick any 3. 7p3. And if you do that on your calculator, and by the way, I'll show you where this button is now in a second, 7p3 comes out as, again, 210. So if you're wondering where it is, it's just over the multiplication button. There it is there. Yeah, and again, it's a second function of the multiplication button, and it works perfectly. So instead of having to say 7 by 6 by 5, let the calculator do it. Just tell the calculator, out of 7 pictures, I want to pick any 3. And the calculator will tell you very quickly that that's 210. Okay. At the Olympic Games, 8 lanes are marked on the running track. Find the number of ways in which the runners in a heat can be allocated to these lanes when there are, number 1, 8 runners. Now, let's listen to that again. So we have 8 lanes and this time 8 runners. So that means all the lanes are available to all the runners. And that's fine. So that's going to give me 8 lanes. 1, 2, 3, 4, 5, 6, 7, 8. I've never mastered drawing squares like that. I have to learn someday. Anyway, if there's 8 lanes and 8 runners, any one of the 8 can go there. But one of those 8 will take that place, leaving 7, eventually leaving 6, 5. You notice what it's going to be again? Yeah. There's no restrictions. What's that? That's 8 factorial. And on your calculator, 8 factorial is 40,320. Quite a lot of ways. Okay. However, 5 runners in the heat and all 8 lanes are available. So again, all 8 lanes are available, but there's 5 runners. So there's 8 lanes available, and I want to pick any 5 out of that, see? So 8p5 on your calculator comes out as 6,720. Very easy. So again, you could have your 5 spaces, or your 8 spaces, I should say, with your 5, and that's 8 spaces, pick 5. That gives you 6,720, 8p5. Okay. Now let's take a look at this. This is more like a question we're going to have in a few minutes from the paper, or from the book. How many ways are there of arranging the letters in the word leaving? Now obviously 1, 2, 3, 4, 5. There are 7 letters. No harm to write that down, so I don't have to go back counting them all the time. And what am I told? Arrange them with no restrictions. Well, what I could do is I could put out the 7 boxes and then any of the 7. Why not just remember there's no restrictions? 7 factorial. And from your calculator, 7 factorial works out as 5,040. Okay. If they must begin with n. Now in a situation like this, we've got to think of the 7 spaces. 1, 2, 3, 4, 5, 6, and 7. So if you're ever in doubt, just draw the boxes out. Must begin with n. There's only one n, so only one letter can go in there. Now the n is used up. That means there are 6, 5, 4, 3, 2, and 1. Do you notice anything? Yeah, that's 6 factorial. So this ends up being 1 times 6 factorial, which is 6 factorial, which comes out as being 720. Okay, next one. They must end with a vowel. Now, first of all, 1, 2, 3, 4, 5, 6, and 7. But they must end with a vowel. How many vowels do we have? 1, 2. We've got 3 vowels. So any one of the 3 vowels can go in there. But notice what I said. Any one of the 3 vowels can go in there. Meaning that there are 6 letters available for the first place. 5, 4, 3, 2, and 1. Which is 6 factorial times 3. And 6 factorial times 3 works out as 2,160. The 3 vowels must be together. Now, think about this. The 3 vowels must be together. That's important. So what I would do in a situation like that is I'd put all the 3 of them into one box. There they are. However, they can jumble around themselves. So you could have EAI, you might have AEI. So therefore, they themselves will be a mini factorial within a larger factorial. So now, if the 3 vowels are in here, doesn't that just leave 4 spaces left to be filled? Yeah. And what's that going to be? Any of the 4 goes there, any of the remaining 3, 2, and 1. So this happens to be 3 factorial by 4 factorial. However, and look at this carefully, those 3 vowels could be in the 2nd place, or they could be in the 3rd place, or they could be in the 4th place. So whilst it is 3 factorial by 4 factorial, there are 5 different places that this 3 factorial can be in. 1, 2, 3, 4, 5. So I have to multiply that by 5. So therefore 3 factorial by 4 factorial by 5 works out as being 720 ways. So you've got to be very careful that you make sure the mini factorial is also moved into the other places as well. Next one, L and N must be side by side. Okay, put them together. There they are. There's the 2 of them. And again, because it could be LN or NL, it's 2 factorial. Meaning what? Yeah, 5 spaces left. 4 and 5. So what does that mean? If the 2 letters are here, L and N, that means there are 5 available to take that position, followed by 4, 3, 2, and 1, which is 2 factorial by 5 factorial. However, that 2 factorial Might be in first place, might be in second place, or third place, or fourth place. So there are 1, 2, 3, 4, 5. There are 6 places that this 2 factorial could actually be in. So I multiply that by the 6 possibilities. And I get 2 factorial by 6 factorial by, 2 factorial, I should say, by 5 factorial by 6. And that comes out as 1,440. Now, this is interesting. L and N must be apart. Do you notice anything? They're opposites. L and N must be together. L and N must be apart. So they're opposites. Isn't it true to say that if L and N aren't together, then they must be apart? So isn't it true to say that if I put these two together, I should get all the permutations of 5040? Now, if all the various different arrangements are 5040, and when L and N are together, that gives 1440, well then obviously the difference between these two must be the number of arrangements where L and N are apart. Just think about that. There's the total number of arrangements. There's the arrangements when L and N are together. So the difference between these two must be when L and N are apart. And when I do that, we get 3,600. Okay, so let's just remove that annotation because I have it already in print. Easier for you to see. I just wanted to work it through with you. So we get 7 factorial for the first one. We get n in the first place multiplied by an arrangement of any of the 6, which is factorial. If they end with a vowel, that means that there's 3 vowels at the end, and then there's 6 other letters being rearranged. The 3 vowels must be together. It's 3 factorial. Then the remaining 4 are 4 factorial. And because the 3 factorial has 5 places to visit, that means that it's multiplied by 5. L and N together, that's 2 factorial. The remaining 5 factorial letters go after that. But the L and N have 6 different places that they could be in, so that's 1440. And finally then, the no restrictions minus the L and N side by side must give me the number of arrangements when L and N are apart. Okay, so here's one for you to do now. And I'm going to put this up here, then you pause your video, you go away and try this yourselves, and then unpause when you're finished. P, Q, R, S, T, and U and V are 7 students. In how many ways can they stand in a row if? Okay, number 1, there's no restrictions. 2, P and Q must be side by side. P and Q must not be together. T, U, V must be beside each other. And P and V must never sit at the end of the row. Okay, pause, do the question, get your answers, and come back. Okay, welcome back. Surely you should have answers in front of you now at this stage. So just very quickly, let me go through this one here. No restrictions. 7 people, 7 factorial, and we've already looked at this. 5040. P and Q must be beside each other, so therefore you put P and Q in there. That means then that there are 5 more spaces to fill, which is another 5 factorial. But because the 2 factorial can be in any of these 6 positions, that's 2 factorial by 5 factorial by 6, which comes out as 1440. Very similar to the question beforehand. P and Q must not be together. Well, if these two, it's the only possibility. P and Q are either together or they're not together. So all of these must be 5040. So if that's the number where P and Q are together, then obviously 5040 minus 1440 is 3600. T, U and V must be beside each other. Now this time, again, 3 factorial. That means the remaining 4 will give me a 4 factorial, which is 1 and 4. There's 5 different spaces, so that's multiplied by 5. So 3 factorial multiplied by 4 factorial multiplied by 5 comes out as 720. And lastly, P or V must never sit at the end of the row. Now, in a situation like that, we've got to look at 7 spaces. Okay, P and V not allowed to sit at the end of the row. What does that mean? That means that there are 5 letters to take first position, one of which will, and there are 4 available for the other end. So you do the ends first. Now, in a situation like that, if there are 4 left here, doesn't that mean then that after the 2 are, the 2 can't be at either end? So that means then obviously that you've 2 used up, which brings you back down to 5. Then 4, 3, 2, and 1. So therefore, when we multiply those together, what are we going to get? 5 5 is 25, times 4 is 100, times 3 is 300, so that's 600, and that is 6 4s, that's 2,400 different ways. So the squares make it very easy to fill in once you understand exactly where the letters have to go. Okay, again, just clear that, and let's put the answers up this way. So as we said already, 5040, 6 by 2 factorial, then we've got 5040 minus 1440, then we've got 5 factorial by 3 factorial, and then we've got the 5 by 5 by 4 by 3 by 2 by 1 by 4. That's what gives me the final figure of, what did I say it was a minute ago? 2400. Okay, now that was for one event. So one batch of numbers, one batch of paintings, one batch of horses, one batch of objects. But what happens when we've got two events? So for example, you might have event E1 and E2, and I call them E1 and E2 just to differentiate between the two. So when two events E1 and E2 happen together, it's important to watch out for the use of the words and the word or. Now the reason for that is because in probability the word and is loaded. It's a function, it's multiplication, and the word or is loaded because it's addition. So let's just take a look at a question. The use of and represents multiplication, told you already, and then the word or represents addition. So if you have event 1 and event 2, then you simply work out their individual numbers and multiply them together. If you're using event 1 or event 2, then you take E1, E2 and you add them together. So there's the two rules I want you to remember when we're moving into two events. So I want you to try this. Think about this for a moment. A bag contains 9 discs numbered from 1 to 9. A disc is drawn from the bag. If the number is prime, then a die is thrown. Now by the way, see die. A die is one of a pair of dice. So dice is plural, die is singular. So when you have mice, do you call one a my? I'm always wondering about that question. Anyway, it doesn't matter. But a die is one, so it seems unusual, but you never say one dice. A dice is a pair or more. A die is one. If the number is non-prime, then a coin is tossed. Coin is tossed? Very good. How many outcomes are possible? Now listen to that again. I'm going to highlight this because this is important. Okay, 9 discs from 1 to 9. Okay, a disc is drawn from the bag. If the number is prime, then the die is thrown. If the number is non-prime, then a coin is tossed. How many outcomes are possible? Okay. Now, let's think about this for a moment. How are we going to work this one out? Well, first of all, there are two experiments taking place. First of all, you're drawing a disc, and then you're either, notice, you're either throwing a die or tossing a coin. There's the word or, which is addition. So if I was to work this out, you could say the following. 1 to 9, that's the first outcome, and then a die is thrown. How many is in that? 6. There are 6 sides on a die, and there are 9 discs. Okay, but if the number is non-prime, then a coin is tossed. So let's write this out and see what it looks like. Prime and a die, they will work together. So if you draw a prime number, you will toss the die. So that's prime and die. Or the other alternative is a non-prime number, and then you toss a coin. Do you hear the words? You draw a prime disc and you throw a die. Or you draw a non-prime and you toss a coin. So if we were to turn these now into numbers, prime and die. Let me just write it out for you. Prime and die. Let me go to pen and black. Okay, prime. How many prime numbers? Prime. Is 1 a prime number? No. 2 is. 2, 3, 5, 7. And what else is prime? That's it, isn't it? 4. So there are 4 primes and a die. How many? 6. Or, so there's the first one. Non-primes. 1, 2, 4, 6, 8. And 9. So 1, 3, sorry, non-primes. 1, 4, 6, 8, and 9. So that's 6 again, and a coin, that's times 2. Am I right in that? Yeah, that's it. So you've got primes, which are 2, then you have 5, so 2, 3, 5, and 7, yeah, and then non-primes are 1, then you have 4, 6, 8 and 9. Okay, so now 4 6s are 24, or 12, which is 36. That's it. So it just takes a little bit of thinking in relation to do this. So let's remove that. Numbers, 4 primes and 6 numbers, are 5 non-primes and 2 sides. So that gives us 24 plus 10, which is equal to 34. Did I say that right? 4 primes. What are the primes? 1, 3, 5 and 7. What are the non-primes? 2, 4, 6, 8, oh, and 9, of course. Yeah, there you go. So it's 5 non-primes and 2 sides. So the 4 primes and the 6 numbers, and then the 5 non-primes and the 2 sides of the coin. So that will give you 4 6s are 24, 5 2s are 10, 24 and 10 are 34. Okay, now over to you. I'm going to stop because I've talked for long enough. I want you to take the following questions from book 2 on page 48, 49, 50. I want you to do them. Come back to me by email if you have any difficulty with them. If not, in our next class we'll go live and we'll go through these questions, making sure you understand exactly where the answers come from. So until the next time we talk, take care and enjoy.